Very good. Right. Right. So the stream is on, and I have about 30 seconds, about 20 seconds before 11 o'clock at our time. So Dominic, I'll let you take over everything.
Thank you. Right, so I'm just doing talking, not handling
Right.
Zoom, I guess.
Oh yeah, and just at the moment that you say here's, before Maxim starts speaking, I'm going to mute everybody, but then Maxim may have to unmute himself. Okay, but that's more advice for Maxim. Okay. So I think we're ready when you are.
So before we start, I'd like to announce a change in program. Unfortunately, Andy Nietzsche has had to withdraw. So for our third talk today at 8 o'clock UK time, we will have Tom Bridgeland's second talk. And then in place of Tom's second talk tomorrow, the first talk will be by Greg Moore, replacing Andy Nietzsche. Okay, so our first talk this afternoon, evening, morning, is Maxim Kontsevich, who needs no introduction, and who'll be talking about analyticity and resurgence. And his slides are available in the chat.
Maxim, unmute yourself. All right, there we go.
Unmute. Okay. Now it's okay?
Yes.
Okay. Yeah. So I'll talk about relation between resurgence and wall crossing, which we and some notion of analytic wall crossing structure, which we discussed with Jan in our recent paper. And it will be a little kind of second version. We will kind of replace our paper soon by improved version. Yeah. So I will start with recalling you a very general notion of stability structure in graded Lie algebra, which is applicable to all situations essentially which we're interested in. So we have some gradient lattice, which will be finite rank free abelian group Z to power n, and we have a Lie algebra over rational numbers or any ring containing rational numbers, which will be graded by this abelian group.
Maxim, your slides are not advancing.
Sorry?
Your slides are not advancing.
Oops, just a second. It's a bit strange. Maybe just.
You may have to stop sharing and start again. Okay. Well,
okay, stop share. Okay. Stop share again.
And then start again.
Yeah. And start again. Yeah. Okay. Strange. Okay. Okay. Now it's okay. You see my first slide, yeah?
Yes. Mm-hmm.
Now maybe you see my second slide.
Yes,
I hope,
there you go. Right. Thank you.
Yeah. Okay. Yeah. So we get gradient lattice, which is free abelian group of finite rank, Z to power n, and Lie algebra over Q, say, which graded by this lattice. And we call this set of stability structures on this graded Lie algebra as set of all possible pairs. Z is a central charge additive map from group to C. And for all this beginning of the story, C can be replaced by oriented R2. It's oriented two-dimensional plane, and a collection of elements in graded components, which are based certain stupid support axiom. Support axiom said that many of them vanish. Namely, there exists a non-degenerate quadratic form actually non-degenerate one can emit, quadratic form on a real vector space R to power n, such that it will stick to the kernel of the map, which is a certain subspace of codimension 0, 1, or 2. The form of this space will be strictly negative. And if you consider value of quadratic form on any lattice vector when this element A gamma is non-zero, then you get strictly positive. And it implies that the set of central values of charges gamma, for which A gamma is non-zero, is a discrete subset of C. So I just show you kind of standard picture which I have in mind. Here, let's imagine like my lattice has rank 3. And so this, if you multiply by R, you get a usual Euclidean space which projects to plane. This green thing is the kernel of the map. And I have quadratic form such that it will be negative on 2 light cones here and positive everywhere else. And the support will be outside of these 2 halves of 2 half cones. And you see immediately that the image is discrete because the projection is kind of proper map and have discrete subset of the complement. And it will be not only discrete, it will be subset with polynomial density. And the density depends on the rank of the lattice. Polynomial infinity density. Okay, that's a typical picture of this support property. Yeah. Now, I want to describe this space of stability structure for given the central charge in a different way. Namely, what we do, we do the following. Let's pick any open sector in our plane R2 with size strictly positive. It's because open, yeah, it's non-empty, and less than 180 degrees. And we define what is GV, the group associated to this open sector. It is it will be actually pre-sheaf, I suppose, in whatever topology. This GV will be inductive limit of certain group associated with other guys called CV, which are some strict closed convex cones in Rn. And the strict convex closed cone is such that if you consider remove 0 from the strict closed cone and take the image, you get a subset of this open sector V, which is this condition implies that this central charge restricted to the cone is a proper map, and the image will be something strictly smaller than V because the image will be closed sector, which is this strict subset. It so never touch boundary of the open sector.
So it's a type of V capital is equal to V small.
Yeah, it's type. Yeah, it was all prepared and half an hour before. Yeah, one should expect certain typos. Yeah, I'll correct them. So it will be certain typos. It will be capital V. Yeah, and this group associated to this closed sector is the pronilpotent group. Namely, you take Lie algebra field, pronilpotent Lie algebra. We consider all elements of gamma, which actually should be not equal to 0. I forgot to type it. Small gamma is not equal to 0. Get corresponding components of my Lie algebra. And because it's strict convex cone, that will be the Lie bracket will be well defined to get pronilpotent Lie algebra, get pronilpotent group. Yeah, so you see this GV is inductive limits of projective limits. Yeah, but kind of in real life situation, when you have element of the group, we get corresponding cone, and so if you can forget about this inductive limit picture. Yeah, so we get this collection of groups associated to open sectors for given central charge. And now take a covering. Yeah, so this picture is a bit small. So we get covering of my C minus 0 by open sectors. And so we ordered in cyclic order and overlap only two consecutive sectors will overlap. And starting from 2, they do not overlap. So we choose such things. Then we get intersection. We again get another open sectors. So we get 2 times capital N open sectors and get 2 to capital N groups, and they form kind of cyclic ordered diagram of inclusions. The group associated to intersections maps to groups to Vi and Vi plus 1. We get the cyclically ordered picture. And then if you get the cyclically ordered picture of groups and subgroups, then one can kind of make some kind of generalized double coset space and consider fibered product of these sets GVI over subgroups acting on the left and the right. And the claim that this space of stabilities is the same as this generalized double cassette construction. The description on the right-hand side depends on the choice of covering, and one can easily identify them for different coverings. So I suppose everybody knows what is going on, but just what will be formal construction. Before I said you have a collection of some elements of Lie algebra, you should maybe make your sectors kind of smaller and decide for each ray in a plane to each of sectors it belongs to. So it will decompose a set of rays and maybe kind of semi-open sector, something like this. And then you take ordered product of exponential, some of the say gamma, get some representatives of GVI. You can have different representatives, so it will be the same element in the double cassette. Okay, that's a very simple theorem, but it gives a kind of nice, clean way to describe what is a kind of right topology on space of stability structures. I recall that if you get stability structure in Lie algebra, you can vary a little bit central charge, and what a little bit depends on this support, this quadratic form which you start with. And then if you vary a little bit central charge, you can kind of make a parallel transport of this elements of gamma in a certain way. Usually when originally we thought about this, it was kind of like divided by infinitely many steps, kind of very, very small steps, and decompose elements in some order. But one can describe in some much cleaner way. Namely, let's just choose a covering, a stability structure, and some representatives. Some representatives given by just collection of these convex cones and elements in the corresponding group. As there are other representatives, get different cones, different representatives. But if you choose one, then the fundamental system of neighborhoods I'll declare topology will be the following. We vary a little bit the central charge and keep both this data the same. So covering will be the same. This cones will be the same. AI will be the same. What happens if we vary the central charge a little bit? These cones, because they project to something closed inside VI, we still project to something inside VI because they don't touch the boundary. So it will define for nearby central charges. And in this way, this space of stabilities becomes a Hausdorff complex manifold. And this forgetting map, if we just consider the central charge, will be local analytic isomorphism between this domain and Cn. Yeah, so it's a nice simple reformulation. We have some other reformulations as well. This also works for certain generalization which appears in real life. Namely, in some situations, you don't have a lattice, but you have a local system of lattices. And the monodromy will be usually some quasi-unipotent monodromy, like usual in algebraic geometry. And Lie algebras will be also not one Lie algebra, but local system of Lie algebras. And it appears for WKB limits for irregular singularities. So you don't have just one story, but I will not use this generalization in my talk, but one can keep it in mind. Okay. Now, Now I go to the main notion. What is analytic stability structure? Yeah, from now on, I assume that Lie algebra is the algebra of polynomial vector fields on a standard torus. So it considers formal finite sums. We get certain complex numbers, a gamma j, get some monomials, x to power gamma, and get basis of Lie algebra vector fields in torus. So you see the dimension. This gamma will be actually grading, and dimension of g gamma will be n, because it will be spanned by this xj or d xj. Yeah, so it's a bit different from this Poisson Lie algebras which we are used to, and dimension of g gamma is 1, for which it's n. Yeah, yeah, it's bigger than they're not Hamiltonian vector fields, it's just all vector fields, but it's sufficient for what is called 2D and 4D well crossing. So we have like Poisson maps, it's part of the story, or if it's Poisson structure is degenerate, you add some kind of dual variables. And if you have 2D well crossing, like in Chakotay-Vafa or exponential integrals, you get something like automorphism of trivial vector bundle on you add to symplectomorphisms also gauge transformation and trivial certain vector bundle, certain rank on the torus. But because it's trivial, we can introduce again coordinates and in the fiber, and can be a bit stupid to replace vector space by tori, but the whole story works. Okay. Yeah, so just maybe to say why you consider this generality with Jan. Yeah, we thought it's kind of first nice way to combine together 2D, 4D well crossing, but at the very end, it turns out it's really important. We have case n equal 1, which is kind of non-interesting neither from 2D nor 4D well crossing story, but still get diffeomorphism in one variable, and it's related to something called the Kal-Varonian theory. Okay, which is some story about resurgence. Okay, so what is analytic stability structure? So from now on, my Lie algebra is just vector fields. It's the definition is the following: there exist representative for some covering. Yeah, so at the end of the day, the definition doesn't depend on the choice of covering. So that each transformation AI is analytic. What does this mean? Because there are finitely many, we can choose some overall constant. And such if you write the transformation as a map, xj goes to xj times something, and these monomials lie always in a cone, -0, then the coefficients obey some exponential growth. Okay. Yeah, so it's a definition. It doesn't mean that elements A gamma, which I used before, have exponential growth. It's a different property. If originally, as I recall you that it's given by some elements in my Lie algebras, if they have exponential growth and support properties, then this transformation will have exponential growth. But I don't know whether the converse is true. So with Jan, we tried for several years actually to prove it. If you decompose in clockwise order this analytic transformations and take logarithms, get exponential growth. It's very, very complicated combinatorial question. We take sum over trees story, and we got lost, I have to say. So maybe it's true, maybe not. I have no idea. Okay, what are potential examples and non-examples of analytical crossing structure? Yeah, in fact, it's from Grant perspective, it's very special property, and it's very, very not general at all, but good in some situations. Yeah, so one can talk, for example, about misprints, about DT invariants for 3 Calabi-Yau categories. And there are several groups of examples which you can have in mind. Yeah, so if you are algebraically inclined, you'll start with quivers with potentials. And there are some quivers. Yeah, for example, we have quivers with generic potentials. It's a series of cluster algebras. And if you consider quivers which are derived equivalent to acyclic quivers with some stability structure, which you obtain by deformations, it's always whenever how far you move in space of stability conditions, you get analytical crossing structures. And in fact, it will be something even more. It will be what we Jan call rational. And in particular, for if you get a central charge with let's say this is rational, maps to lattice to Gaussian integers, consider preimage of rational cones, the transformation will be algebraic maps. Yeah, so it's something that's very much under control what's going on. Get some algebraicity here. Then one can have some other interesting quivers with potential. You can see the non-oriented graph. And this non-oriented graph gives rise to two Calabi categories, a collection of spherical objects. It's not quiver, it's just a non-oriented graph without loops. And the potential it's well known how to one can lift it to three Calabi category, namely one double each arrow by arrow, each edge by replaced by h by two opposite arrows, and add a loop at each vertex and get some cubic potential. And it's the equation's formally the same as for Nakajima varieties, but we treat it as a complex representations, not real representations. And the whole story is related to something called Katz conjecture about Katz-Moody algebras. Victor Katz many years ago guessed that you count something for a quiver like absolute reduced representation, get polynomials and number of elements of finite field, and he conjectured it has positive non-negative integer coefficients. And fortunately, a few years ago, it was solved using this wall crossing structures, DT invariants. And a postdoc at HS, Jean Ren, she calculated kind of a couple of weeks ago, like for Kronecker quivers, two vertices and three arrows. She calculated sufficiently many numbers, and what one can see from these numbers that if you consider dimension of Katz-Moody algebra, it grows exponentially, but at values of Katz polynomial q equals 0. But if take actually value at q equal 1, we get faster than exponential growth. Yeah, so it's something interesting here goes on. So it's definitely not analytic wall crossing structure. Yeah, these numbers are not known in any hyperbolic case, I suppose. Yeah, then there is among the quivers with potential, there's also some kind of nice class with associated with what is Jan called Strebel points in Hitchin bases. Strebel, when you have Hitchin integrable system associated with some spectral curve and so on, then I am interested in points when on spectral curve this canonical one form has all real periods. These are very special points, which for rank 2, in some cases, Strebel differentials, or it's even for rank 2, it's something new. And we have conjectured this point is unique if it exists and unique, if all residues are real. And a conjectural picture, when you get the Strebel point, then you should get certain quiver with potential. And so this will be, and in this case, Evsker should be fine. And these are essentially examples which people play with in this game. Because this also, from other perspectives, this is also Foucault category of certain non-compact Calabi threefold, which are associated to Hitchin integrable systems. Or if some people like B model, you consider coherent sheaves on non-compact Calabi threefold with support on certain curves, singular curves or singular surfaces. this should be mirrored all to the same story. But stability, it's kind of more natural from point of view of Foucault categories. But now if you consider Foucault categories of compact color with threefold, we definitely expect the answer will be no, since it will be not analytic, because Aguri-Stromer-Girard conjecture said that this DT invariants grow like exponent of square of norm of vector. Yeah, I think what they meant was this is called something like attractor points. There are some canonical DT invariants as to gamma, and this constant related to this by mere symmetry, the shape of a Lagrangian cone, this kind of function of zero. So this, so from this, its constant depends on direction of gamma, and when you study the dependence, you get variation of hot structures. Yeah, so it's deep conjecture, and this, as far as I know, it wasn't checked at all. Yeah, there are some special cases where people, for some rigid Calabi-Yau, has the idea what a Donaldson-Thomas invariants look like. They have some guesses through some automorphic forms, and presumably in this case it will be topology. But in general, you see something faster than exponential, so it will be no analytic germs of analytic transformations whatsoever. Okay. Now, what is our main result in paper with Jan? The theorem that the property of stability structure to be analytic is open and closed. So it's invariant under deformation. It's property of connected components of space of stability structures. Openness, it just follows from the definition, but closeness, it's really tricky part. Yeah, in fact, we developed some notions of like algebraic, rational, and polynomial stability structure, and I forgot exact status. We have kind of similar theorems, but they based on they are not theorems. They are based on some result which we do not know how to prove in complex in analytic geometry.
In fact, non-Archimedean.
Actually, non-Archimedean geometry, yeah. Yeah, maybe I'll tell you later what is the result. And from the proof and causal analytic story, we see that analytic stability structure gives rise to two completely different complex analytic objects. They have something common part, but they're really different. Again, in real life examples in Hitchin system, you can identify with familiar objects. And the second analytic object will be related to resurgence and Ecale resurgence. But actually, if you return to the previous slide, when I said that you get examples and non-examples, yeah, get many things which close exponent quadratically. What will be the analytic object? So the physics, in fact, predicts something for three-dimensional Calabi-Yau, if I'm correct, that one should use not DT invariants, but refined DT invariants. So you get some second index, giving some quantization. And it looks that it gives rise to quaternionic Kähler manifold, which is some differential geometric structure, which will be some kind of holomorphic contact manifold. It gives a holomorphic contact manifold, which will be one more complex dimension. But this quaternionic Kähler manifold, which we'll see, it will be kind of like germ at infinity. In germ at infinity, it will be look like a total space of what's called Danagi-Markman integrable system, associated with Calabi-Yau threefold. It's kind of bundle of a Lagrangian torus with fiber intermediate Jacobians. But this kind of divides at infinity, and not really divides because the things not converge. And something like S-duality says that its germ at infinity fills from inside to something compact quaternionic Kähler variety. Yeah, so it's maybe even to formulate what is going on, this exponential quadratic growth will be sufficient, but that I didn't check. Yeah, okay. Yeah, so now go to exponential growth. So the openness, as I told you, is obvious, but the closeness, even in dependence on the choice of covering, is not at all. It's not close at all. So let's see what's going on. We have cones in Rn, yeah, for these representatives. And these cones can overlap. And we can always modify that they form some kind of like, there will be rational polyhedral cones, and each neighboring cones intersect along the face. So it will be like touch each other in cyclic ordered way. Then, so hence we get a FN, yeah, just collection of rational polyhedral cones and their faces. And hence we get a non-compact toric variety. And this non-compact toric variety will contain what? Each had a top dimensional cone will correspond to 0-dimensional strata, and each n-dimensional face correspond to 1-dimensional strata. So we get a wheel of CP1s. And it's stratified by historic strata. So we get kind of compact part of this, a wheel of CP1s, and some kind of neighborhood of it. What is formal stability structure? When we ignore completely convergence issues. One can easily see that formal stability structure is the same as deformation of formal neighborhood of this wheel, preserving stratification, and I forgot to say maybe preserving first jet along the wheel. And we will see that analytic stability structure will be analytic germs with stratification around the wheel of CP1s. Yeah. So what happens if we have this wheel of polyhedral cones? Then we get certain canonical representatives, and canonical representatives will be twice as many as we have before, because we will be representatives associated to the intersections and with strict interiors of the cones. So when we take logarithm, we get no monomials on the boundary. And when we are try to arrange these things to elements associated to the cones VI itself, we can put, for example, this CVI intersect with CVI plus 1, this common face, either to VI to VI plus 1. We can associate to one piece or another, but if you don't associate, we get kind of 2 times n canonical elements. Yeah, it's again very easy to see this canonical representatives really don't depends. If you choose these cones, they're unique. There's no ambiguity. And the claim is analyticity of my thinking, in my definition, it's the same as analyticity of canonical representatives for some given polyhedral covering. Yeah, so how to see that some representatives are analytic, then this canonical representatives, why this properties are equivalent to each other. Actually, it's already used to some kind of basic lemma. Basic fact about analytic transformations. Let's consider any rational polyhedral cone and cut by hyperplane, rational hyperplane, in 3 pieces. Kind of C0 will be intersection. C0 will be intersectional plane, C minus will be on the left, and C plus will be on the right. And then we consider this transformation analytic in the sense which I explained in left, right, and in the middle. We take 3 subgroups, and the claim the big group is, as said theoretically, is a product uniquely, each element is uniquely decompose the product of these analytic guys. It's clear the product of 3 analytic elements is analytic, but it's not clear why analytic elements which decompose canonically in the product of 3 things, all factors will be analytic. Yeah, and what is the basic idea? Actually, this idea goes back already several years ago when I proved algebraicity of certain maps and in same situations. And one can try to geometrically interpret where all this change of coordinates come from and why this decomposition in 3 pieces. And eventually it boils down to the following situation. We have, let's say, certain chain or wheel or even chain of CP1s and with some stratification around, look like a toric variety, and we deformed it as an analytic variety. We get some kind of analytic space with stratification. Then we can make several other toric blowups, and then we get 2 divisors, which sits very far from each other. And after making these blowups, we get certain chain of CP1 toric kind of strata, which connects one divisor to another divisor. And then what happens? This union of this finitely many P1s, it's look like degenerate P1. It's kind of semi-stable curve, and then it can be we can try to deform it. Everything could be done in form power series, and in appropriate situation, we get appropriate position of vectors in lattices and so on. This union of CP1s will be deformed to smooth to just family of one smooth CP1, which will break down in the limit to a single one. And this family will be a universal n-1 parameter family, which identify points open part of one divisor, open part of another divisor, and give some kind of global coordinates in some domain. And when consider another family of P1s, you get another global coordinates, and change of coordinates will be these canonical transformations. But now what happens in our situation when we go from form power series to analytic germs? From analytic series, we get this formal family of P1s, which is n-1 dimensional. But because we are in analytic variety, we can apply Duadis theory of Duadis spaces. It's kind of analog of Hilbert's scheme. Closed analytic subspace form again analytic space. And then we see that we get a formal germ, it will be actual germ. And then we get actual coordinates somewhere, and we have another family of P1 gives another coordinates. And on overlap, you get change of coordinates. Yeah, that's a rough idea how it goes. Yeah, and so the whole story, to get this change of coordinates, you should consider these families of P1s. And instead, you get families of C stars in your variety. And what happens for Hitchin system? So it's actually very nice, beautiful algebraic question. What here really goes on? Where we get these wheels of CP1s and so on, we consider what's called Betty modular space. Let's forget a surface with mark points or maybe regular data, whatever, some group. Yeah, you consider this modular space of local systems, which will be some algebraic variety over integers. It will be some kind of cluster variety, typically. It's called character variety if you consider representation from the fundamental group. And it's algebraic variety with volume element, and it's kind of local ABR. One can consider its partial compactifications when volume force has poles of first order. And in this partial compactification, it's very combinatorial objects because there are only countably many divisors to speak about. There's no continuous parameter. You can choose partial compactification, you get some strata, and we can choose a wheel of CP1 at infinity. And that's what we expect, what is really goes on. You get this wheel of CP1 at infinity. You consider it's in some partial compactification, get stratified space. You consider tubular neighborhood, small neighborhood. If you consider formally, you get formal neighborhood, and it gives stability structure. And because it's actual analytic object, it gets analytic stability structure in our sense. And now, to make these coordinates, we should move kind of C star inside this modular space, and because everything is algebraic, so what happens? You get family n-1 parameter, n is the dimension of this Betty modular space, of C stars mapped to Betty modular space. And what is map of C star to modular space? It's a representation of fundamental surface on fundamental group in Laurent polynomials in one variable, with will be coordinates along this T. Yeah, so in this example, one can really construct it. You get certain nice families of these maps. They depend on n-1 parameters. Then you give some kind of coordinates on Betti moduli space. Will be T and this extra n-1 parameters. And if you consider change of coordinates from one such covering family of C star from another family of C star, then you get certain algebraic maps, which will be exactly this DT, whatever, elements A, C, V associated with certain big polyhedral cones somewhere. It will be and then you get algebraic maps of very big degree. Okay. Yeah, what is the second analytic space which we don't have around and how it's related to the questions of resurgence? Yeah, so now let me give this very simple construction. Yeah, so suppose we have analytic stability structure and Maillet algebra is again change of coordinates in torus. And I draw several cuts in plane which will be not plane of central charge, but what's h bar plane, and h bar will be Planck constant. In fact, it's end of the same plane, but I want to denote the coordinates by different letter. Yeah, so one can draw several cuts. It's enough to have 3 cuts just by 180 degrees. It could be just sector should be just less than 180 degrees. Yeah, consider 3 cuts and 3 or 4 cuts, as you like, and consider a trivial bundle. The fiber will be torus with coordinates x1, xn, and the base will be C with coordinate h bar. And along this cut, modify this bundle by the following change of coordinates. It's kind of the same change of coordinates which you have before, but we multiply by these characters, exponent minus the gamma of h bar. And we assume that along the cut, when h bar stay along the cut, and gamma stay in this convex cone, the real parts of these things will be positive and go to plus infinity. So it means that when h bar will be very close to 0 along the cut, it will be very fast convergent series. And exactly exponential growth will guarantee that for given x, for small h bar, these things will be very close to 0. It will be convergent close to 0. It will make sense. Yeah, so you see, you get original transformation. You just conjugate by multiplicative shift, by the multiplicative shift. Okay. Yeah, so make this modification. Yeah, so it's actually rigorous construction. What do we mean? Make cuts, modify, but what do you do at 0? Of course, you can do it outside of 0, but what do you do at 0? It's actually very easy because first we make on the total space real blow up in a complex hypersurface h bar equal to 0. It's a central fiber. We take oriented real blow up. We get real manifold with boundary. And okay, then we have sheaf of functions, C infinity functions. When we make a cut, the cut, you see the transformations you make, it has exponential decay, so it will be in terms of kind of Taylor series, it will be trivial transformation. So it will make sense on this sheaf of C infinity functions, so it's okay. So we can make the 6, and we get variety with C infinity structure. Then we can mod out by S1 action and go back from real blow up to back to itself. We get C infinity variety. You get variety C infinity structure. And then outside of our central fiber, we'll get almost complex structure, which is integrable. And then you can see that get almost complex structure, which is C infinity everywhere. And then I apply Nuremberg theorem. Yeah, but it's really much to say about nothing. Yeah, but yeah, so you can really make complex varieties by this phase of formulas which do not make sense exactly in central fiber, but everything is well defined. So we get a holomorphic submersion for certain n+1 dimensional variety to my CH. And this, it's actually not a bundle because its fibers are not compact. It doesn't make sense to speak about this as a locally trivial bundle. It's just submersion. And it will be, if you restrict to form power series of H bar, it will be canonically trivialized, because this change of coordinates has trivial Taylor coefficients at 0. Yeah, so this thing, it's actually not actual variety, it's only germ of complex manifold at the central fiber. And the central fiber is not compact, so it means that kind of you choose, if you take point in C star to power n, some points x1, xn, then the size of neighborhood in H bar direction depends on this point. If you go far to infinity in your torus, because it's uncompact, then the size in H bar will be smaller and smaller. So it's such a guy. And what is this variety in again real life examples? So we consider, for example, twistor family, or not really twistor family. It's called maybe conformal limit family in general. So H bar for over H bar equal to 0, we put as a fiber, say, Hitchin moduli space, like bundles with Higgs bundles, and for H bar not equal to 0, get Betti moduli space. And so one will be limit of another. The fiber at 0 is not a torus at all. Yeah, it's something else. But now it contains a certain subvariety. Hitchin moduli space contains a abelian variety, some fiber of Hitchin. If you take point on the base of Hitchin system, take a fiber, you get a abelian variety. It will be, and consider it as a subvariety in a total space of this twistor family, and make blow up, holomorphic blow ups there. Then I get exceptional divisors, which will be something like vector bundle of abelian variety, trivial cotangent bundle of abelian variety. And cotangent bundle of abelian variety is a complex variety, is the same as C star to power n. Yeah, so you get, it's actually get twisted cotangent bundle. Yes, so you get C star to power n. And so you see the stuff to blow up, you get C star to power n, and consider neighborhood of kind of germ of this is star power n. Then we get the second analytic space. Yeah, maybe before I go on, I just want to say that on this, you have this bundle H bar X goes to CH, this holomorphic submersion. You see that, let's go back to this story. We see that from H bar non equal to 0, if you consider go to coordinates, if you rescale coordinates by exponent z bar of H, you get transformation which you don't depend on H bar. So it means that in rescaled coordinates, one can define kind of like foliations, so that rescaled coordinates stay the same. And this gives you what? This gives you on this bundle, and the transformation preserves this foliation. So it means that you get this holomorphic submersion, and you get a kind of meromorphic connection, non-linear connection, this guy, which has a kind of second order pole when H bar goes to 0. Yeah, so you get a bundle with over, let's say, small disk with holomorphic non-linear connection. That's not, in fact, we have again some hypothetical description, which we didn't put on my slides. Still another formulation, what is stability, analytic stability structure. It's essentially this bundle with this connection, but it seems to be not sufficient data to really see why it's analytic stability structure. We should go kind of like universal family of a certain domain in moduli spaces of central charges. So you get something like n-dimensional bundle over n+1 dimensional base. It will be a small disk in H bar and small neighborhood in space of central charges. And outside of H bar equals 0, you get non-linear flat connection with certain properties with certain residue, leading term. One can form these properties, and we expect it will be exactly the same as analytic stability structure. So the support property one can read back from size of neighborhood in a domain of central charges. Yeah, so it will be certain purely geometric, like in foliations, singular connections, analytic connection type reformulation of what is going on. And now I'll finish with I think its relation to resurgence. It's we have made this kind of main conjecture. In the above situation, we make the second analytic space and consider any germ, holomorphic germ of a section. Then in formal optimization, form power series, we just got certain formal power series xj of h bar, and it will be some initial point multiplied by some series in h bar with numerical coefficients. And we expect this guys will be resurgent series. So Borel transform will have all nice properties, whatever you want. So there's case of n equal to 1. Actually, it's a very interesting case. It's one of the first examples of resurgence. It's called a Kal-Varonian theory. So in this case, lattice is Z. When you get map, you get two rays, essentially two rays, and you get just two germs of analytic maps and one variable. What will be analytic stability structure? You get kind of, positive integers, negative integers. You get some two germs of analytic function and variable, and there was a theory by Fatou that it's the same as conjugacy classes of germs of certain analytic maps in one variable. Z goes to Z.
I have a question.
Yeah.
We seem to have two ends. When you say n equals 1, do you mean the dimension of the torus, not the ends?
Sorry. It's wrong. And it's maybe called it M. It's not dimension of a torus at all.
Okay, thank you.
No, in the sum it's just another index. Yeah. And now n equal to 1, sorry, it's real dimension. Yes, sorry, I was in bit in haste. I'll correct my slides. Yeah. So I get a Kal-Varonian theory, and it was, I think for Kal, it was really the first example for resurgence. You get some kind of like change of coordinates, making normal forms of certain germs. And if you analyze what is going on, it turns out exactly this germs with section our constructions. It's really one-to-one correspondence. And in fact, when Malgrand gave a talk many years on Bourbaki's seminar, he explained this Ekal theory and this Kal-Varonian theory first. He also used was this cuts and glues. He used the same argument as we use this Müller-Nirenberg theorem, this real blow up and so on. Yeah, the same story. Yeah, so it was really from the very beginning. And for the general dimension, yeah, it's kind of looks the generalization of Kal-Varonian theory. And with David Sauzan, we kind of have a plan how to do it. So we get certain kind of stupid perturbation series, certain sum over trees of certain explicit integrals, and it seems that these estimates will work, and you get convergence. You get kind of infinite sum of resurgent series, which have singularities in a bit more and more poles and Borel transforms, but one gets some kind of like uniform estimates, and the whole sum will be okay, because it will be sum of kind of very fast convergent series of resurgent guys with very good control. Yeah, and so the whole picture, it will be just you get several cuts, you get this change of coordinates as I wrote before, and make holomorphic section. It will be geometric reformulation of very common class of resurgent series, which we have in WKB, all WKB problems, and also the same kind of things will be like for Chern-Simons invariants, quantum Chern-Simons invariants, and not invariants will be the same types of resurgence. There are other more complicated resurgent behavior, which like Penn-Leber 1, which seems to be not of this class, although the lattice is of rank 1. It seems to be something else. next level of complexity. But this kind of finite dimensional objects, just finite collection of series with support in several cones, will gives you description of resurgence. So if one treats it as kind of axioms, this master conjecture, then one probably just have to construct this glued space. Thank you.
Well, let's say thank you to Maxim.
Yeah, maybe. Yeah, I stop share maybe. Or maybe some people have questions to some slides. I can go back to slides. Yeah.
Okay. So, do we have any questions? Yeah, Marco.
Hi. Thanks.
Yeah.
In the case of n equals 1, can you can you explain a little bit more clearly what the second analytic space is?
It's really no difference. You just make a cut. What's going on? You consider. Yeah, I can't really say more. You have product of C cross times CH. You have just one variable x1. Yeah.
Yeah.
The central charge will be like integers. This will be integer numbers. So your n will be equal n. So yeah. And you get along the fiber you make this stupid along the cut you glue up and things x goes to x plus whatever this series very close to identity depending on h bar and another cut. Yeah, no, the formulas is really no special case for.
I guess it's clear what the cutting and gluing procedure produces away from h bar is equal to 0, but I'm wondering about the central fiber.
No, that's really nothing. The story is that because you get these transformations which are so close to 0, it will be trivial, identical transformation trivial on special fiber. In h bar equal to 0, you get just 0. Exponent minus infinity, you get 0. These things will disappear. Yeah, kind of said theoretically, it's clear. You just at special fiber, and then you could put C infinity structure because.
And where does the cycle of P1s appear?
There's no cycle of P1s here.
It's only
the cycle. Yeah, the cycle of P1s doesn't appear here at all. The cycle of P1s appear when you get rank of lattice is 2.
Right, I see.
Central charge is 2. Yeah, if I kind of was a bit in haste. All this picture with cycles was for rank 2, at least 2, and for rank 1, you don't do it. Yeah, in sense, yeah, it's kind of a different story. Yeah, one can maybe add some dummy variables and get some cycles of P1 somewhere, but.
Okay, thanks.
Does somebody else want to ask a question?
So may I ask you a question?
Okay, yeah.
Yeah, actually two questions. First about this Topology story which you mentioned.
Yes, yeah.
All right. So then geometrically we have like K3 or C square. There are two possibilities. Yeah.
Yeah.
And
no.
So
I consider not geometric situation at all. I consider.
No, you don't, but you can. Yeah. Like.
No, if it's geometric, of course it will be. Yeah, for case 3, I don't know. But
C square is still, it's like quiver with potential. Yeah.
Yeah.
So then what you have McMahon.
Yes, McMahon. Yeah, maybe Thomas
and
will
this
talk
is
about
non-analytic, and this is non-analytic.
No, it's analytic.
Yeah, so then it's a bit contradictory.
No, it's McMahon's analytic. No. But I claim that for hyperbolic, for Kazmudi algebras, you get non.
Only
like Kronecker quiver with 3 arrows.
Yeah. This and the second question. Okay, it's clear. And the second question about this related to quaternionic Keller story, or more generally to the appearance of this parameter Q, like motivic or whatever, like comes from the C star action. Should it be treated as a number or as a parameter? And if it's a parameter, so should we think
I really have no idea, because when I do quantum transformations about analytic exponential growth, really little bit worry. Yeah, maybe no, at least definitely if this absolute value of Q is equal to 1 can make the same exponential bounds, but it's only on unit circle. But in principle, yeah, and the trouble if you try to, if absolute value of Q not equal to 1, it depends how you order variables, you get exponent of quadratic growth. Yeah, so it's, you immediately go to a kind of different realm of exponent of quadratic growth. Yeah, that I really don't know.
But if you want, for example, if I want to treat Q as a parameter.
Yes, yeah. Somehow I think we discuss it. We should kind of trade these quantum transformations, which look like you get extra variable, extra index, you get two contact transformations.
Yeah.
Yeah, I don't know how exactly, but it looks that you get right number of indices in both cases. And
yeah, but in the end, this whatever n+1 dimensional object, it will be sort of a piece of the twistor family for the quaternion Keller, so it will be like
yes, yeah, it will be total or dimensional manifold. Yeah.
All right, thank you.
Okay.
So, can I ask, you started by setting up stability structures over a Lie algebra, graded over your lattice, and then you restricted to the case in which the Lie algebra is vector fields on your torus.
Yes, yeah.
Do you have other classes of graded Lie algebras for which you can perform a similar story? For example, Kac-Moody algebras.
I get some notion of analyticity, yeah. I have no idea. Yeah, really only about change of variables. I have really no other. Yeah, maybe one can have something like non-commutative change of variables. Then it's still possible to speak about exponential growth. And this seems to be relevant because at the end of the day, when consider this clustering transformation, we used to think that they use it like simple ectomorphism of tori, but tori are representation of one-dimensional representation of some fundamental group of spectral curve. One can consider kind of arbitrary representation. It will be automorphism of some completed free algebras. That's part of the story which so looking. So one, in fact, we discussed with Jan, we should for some variables assume that it will be freely non-commutative variables.
Are you implying that there might be a version of this story for refined DT invariants rather than for integers? Or
no, refined. It's a different story. It's kind of quantization of moduli space. And what I speak about a representation of fundamental group of spectral curve to matrices of arbitrary rank. It's kind of different story.
So, but again, if absolute value of Q is equal to 1, it's not.
Yeah, if absolute value of Q is equal to 1, yeah, there's no question about this quadratic growth will never appear. Yeah, if you ambiguities and
yeah, Marco.
Just a follow-up question about my first question about the second analytic space. So can you confirm that when you take the C star to the n-1 cross CH bar, is it correct?
No, it's not n-1. I can C star to power n, not n-1.
C star to the power n cross H bar. So can you confirm that the second analytic space is an analytic deformation of that trivial bundle?
Yes, it's analytic deformation of a neighborhood over special fiber 0.
Okay, and so it will not contain the nearby fibers completely.
Not completely, yeah, but for each point of x, for sufficient, in a sense, it will be some neighborhood of this non-compact non-special fiber. But the size of neighborhoods decays when you go to infinity in system.
And the reason that you were invoking Nylander-Nirenberg is because somehow the argument is that you do a real-oriented blow-up, you cut
Yes.
and reglue, and then you notice that at the boundary, the complex structure is exactly unchanged, and so you can blow down.
Yeah, yes, it's infinity in formal neighborhood of boundary, nothing changes. Yeah.
I see. Okay, thank you.
Yeah, maybe just one remark to Marco's question. In the paper, which is in the archive, we have a remark. I just found it. It's remark 4.5.2 about the geometry. And it's like two-dimensional surface with a certain complex one-dimensional foliation, and so on, so on. Maybe it will kind of be useful.
Very nice, thank you.
Okay.
So could we express what you're doing maybe slightly more generally by saying we have a graded Lie algebra which acts as vector fields on a complex manifold, which could be your torus.
Yeah.
And then the analyticity would have to do with series which converge in some compact subsets of this complex manifold.
Maybe, yeah, I don't know. Yeah, no, you want to think me immediately. I cannot think immediately. I can answer the question, which I know answer a priori.
But at least in terms of proofs, it's very much depends on this torus.
Yeah, and this drawing of curves, this is only one non-trivial argument in the whole story. This really family of CP1s. Yeah, that's it.
Are you able to tell us anything about your comment about compact 3 Calabi-Yao's refined DT invariants giving Quaternion Kähler manifolds?
Yeah. No. What do you mean comment? Yeah, it's maybe physicists, if they're present, if somebody can make a comment like grab more, maybe. Yeah. You know. But
okay.
But is the Quaternion Kähler manifold supposed to be the space of stability conditions?
No. It has it has one extra dimension, and it's mysterious object. I think.
Sorry, you're talking. I think you're talking about what physicists would call the hypermultiplet moduli space.
Yes, exactly. Yeah, hypermultiplet moduli space. Yeah, which is and as far as I remember, there was a paper by Boris Piolin and Persson. When they, for some rigid Calabi-Yau threefold, which has no moduli, I suppose. So H3 is of rank 2. So you get lattice Z2, you don't have any wall crossing at all. And they have a guess what are all DT invariants look like through some, again, quaternionic modular form, which is not exactly holomorphic object. And that's probably will give you one example one can study what is going on. So it will be object of kind of series of automorphic forms for some SP4 or whatever.
Okay.
So have a kind of yeah.
Sorry, you go on.
Okay, so I don't want to say anything more. Yeah, so this, as I understand, there is explicit quaternion Kähler manifold associated with some automorphic form with SP4 for this, which you can.
Okay, so
but geometrically, it is related to the quantization of this complex integrable system over the cone in H3.
Yeah, no, this is refined invariance. It gives you kind of quantum modular space.
Yeah, it's
Yeah, but this hypermultiplet, it's nothing quantum related, just some usual variety, and you get twistor manifold, which is usual complex manifold, nothing quantum.
Were you wanting to say something, Tom?
I just want to ask a very simple, kind of trivial question. So this second analytic construction,
Yeah.
I mean, you can contemplate doing this in the case when your Lie algebra is just GLN, right?
Sure, yeah.
And then it looks like it's constructing for you a vector bundle with meromorphic connection, which has
Second order connection, of course, yeah, of course. If you make this linear change of coordinates, okay. For example,
Right.
in this formula, this monomial xj multiplied by x gamma should be another coordinate. X to power gamma will be ratio of two monomials, something divided by xj. Then I got linear change of coordinates. Definitely,
Right.
yeah.
But then you're basically inverting the Riemann-Hilbert map, right? Because you're constructing a vector bundle which has given Stokes data, right? You're sort of
Yes, yeah, just straight on a nose, yeah. You construct straight on a nose this vector bundle, of course.
Yeah, I mean, was that known? I mean, that seems kind of an already surprising thing that you can just explicitly invert the Riemann-Hilbert map like this, just by using.
No,
this
but this is a Riemann-Hilbert problem. How kind of people doing analysis do it? You have...
Right. Okay. Fair enough.
It's a real tautology in a sense. Yeah.
Sorry, could you explain that again in shorter words?
Well, I think in the case when you take a finite dimensional Lie algebra like GLN, this stability structure.
Just a second. Somebody is knocking on my door. I want to. Sorry. Yeah. Okay.
Well,
okay. I'm back. Yeah.
I was just asking my question more slowly. But in the case of a finite dimensional Lie algebra, this stability structure is encoding Stokes data, right? I mean, I think.
Yeah, no, I don't know about Lie algebras. For GLN, yeah, you consider if you contemplate this formula, but x to power gamma will be x to xk divided by xj. You get just linear change of variables. Yeah, that's it.
Like
so you're talking about placing
integral.
the gradient algebra by the finite dimensional Lie algebra.
Yeah, my matrices. Yeah, my matrices. Yeah.
Okay.
Yeah, that's indeed like Stokes automorphism for.
Exactly, yeah.
For the differential equation, which sets, for example, for exponential integrals, yeah, and finite.
So, I mean, this space is some clever way of making something such that the solutions to the Riemann-Hilbert problems are just sections of the resulting projection, right?
Yeah.
Seems, that's cool. Anyway, that's the end of my question. Thank you.
Okay. Okay, so
well, should we declare a break until 1/2 when Marcus Marinho is going to be talking?
Okay,
so let's thank Marcus Maxim again.